Previously, I noted how if I were to jump off the top of a ladder, it is going to hurt a lot more than if I were to jump off the bottom of a ladder, because the more time I spend falling, the faster I'm going to fall. I then asked a bunch of different globe earthers, if the Earth is a globe, and the ISS is continually falling around the world, why isn't it increasing in speed? The globe earthers gave me a wide range of different answers to that. Now please listen carefully to how Wernher von Braun describes orbital mechanics.
Now, what exactly makes an orbit tick? Imagine you put a gun on top of a mountain and fire it in horizontal direction. The gravitational pull of the Earth will pull the bullet down towards the ground, and after having traveled a certain distance, the bullet will finally strike the ground. Now, as we increase the muzzle velocity, the bullet will travel farther. And at a certain speed, the curvature caused by the gravitational pull of the Earth, which pulls the bullet down, will exactly match the curvature of the Earth. The bullet will then keep on flying around the Earth and will fall and fall, never being able to reach the surface of the Earth until it finally hits the breech of the gun from the rear. This is an orbit. You can establish such orbits at various altitudes. Theoretically, you could establish one immediately above the ground, but of course interference with the atmosphere would slow the bullet down and the orbit wouldn't be stable. So we have to go outside of the atmosphere. But once we are outside of the atmosphere, we have a free choice of any altitude we want. And the higher we go, the slower will be the velocity required to balance the gravitational pull of the Earth.
Balance the gravitational pull of the Earth. Now pay attention to the way he describes what that means.
For it is the centrifugal force in the curved orbit that cancels the gravitational pull of the Earth and keeps the object in its stable orbit.
For it is the centripetal force in the curved orbit that cancels the gravitational pull of the Earth and keeps the object in its stable orbit. So gravitational force is a force that needs to be canceled in order for orbit to be achieved. And when it gets canceled out, so that it doesn't decrease in altitude, that is what is considered a balanced orbit.
The moon has been doing this for a number of million years, and the Earth is orbiting around the sun, so the principle is well known and proven in Mother Nature's pattern of things.
All right. So in order to achieve an orbit to where this yellow ball will not spiral down to the ground, the pull of gravity represented by this arrow needs to be canceled out by another force. And if there is another force coming upward that will cancel it out, yeah, sure, that could possibly prevent the ISS from gaining speed. But what force did he claim was canceling out the force of gravity? Let's listen to that again real quick.
For it is the centrifugal force in the curved orbit that cancels the gravitational pull of the Earth and keeps the object in its stable orbit.
He said centripetal, right? Or did he say centrifugal, which is another pronunciation for centrifugal force?
Centrifugal force, or sometimes mispronounced centrifugal force.
Centrifugal or centrifugal.
All right. So it turns out there's no such thing as centrifugal force.
It's fictitious. It's an illusion.
It's the word we give to this thing that feels like a force operating on you if you are the water in that bucket.
Ready? Yep. All right, let's do this.
What's happening is, because you're getting spun, you have an urge to fly off at a tangent of that circle. Okay? That urge to fly off that is prevented, you will feel as a centrifugal force.
So in this instance, the bucket and the weight of the water is what is preventing the water from flying off.
Those two together are what we call a centripetal or center-seeking force.
So the weight and the bucket are creating the illusion of centrifugal force, and the real force in play is centripetal force.
Notice that there is no force acting on the ball that goes directly outward, away from the center. What we often hear called a centrifugal or centrifugal force. You know, the force you seem to feel when you lock hands with someone and you both spin around and you feel pulled straight back, or when a car you're in turns quickly and you're suddenly thrown away from the center. The thing is, this seemingly outward directed force isn't a force at all. It's actually just an object's inertia, the path the object would take if no other forces acted on it, being blocked by a force, a centripetal force.
So it doesn't really matter which one von Braun said, since centripetal force and centrifugal force are actually the same thing in the end. Perhaps this is why people tend to mesh those two together and just say centrifugal. So, in order for orbit to be achieved, gravity needs to get cancelled out by what?
For it is the centrifugal force in the curved orbit that cancels the gravitational pull of the Earth and keeps the object in its stable orbit.
Gravity has to get cancelled out by centripetal force, which in this case is gravity. So according to von Braun, the downward force of gravity gets cancelled out by the downward force of gravity and prevents the satellite from spiraling down to the Earth. Please tell me you see what is wrong with this picture. There is no upward force canceling out the downward force.
He knows a lot about all kinds of stuff. Professor Dave explains.
So how do these objects stay up there instead of falling to the Earth? It's not because there's no gravity. In truth, gravity is almost as strong in low Earth orbit as it is on the surface of the Earth. The reality is that these objects are, in fact, falling to the Earth. It's simply that they are moving so incredibly fast that they fall to the Earth at the same rate that Earth's curvature is produced, always falling but never landing. This is why astronauts experience weightlessness, because they are literally in free fall.
Therefore, they should be continually increasing in speed since there is no force to prevent gravity from causing them to do so. People love to use this whole ball and string example to demonstrate their understanding of how orbits work. But what gets overlooked in this is the fact that the string doesn't reel the ball inward. And since gravity would reel the ball inward, this whole example is a misdirection. Now, here is a yellow ball with one force acting on it. As such, it is an imbalanced force, and since the ball has nothing to oppose it, that ball should move downward. And when an equal and opposite force is introduced, that is when we have balanced forces, and that ball shouldn't move anywhere. When we add a third force, we have one set of balanced forces and an imbalanced force, so that ball should move straight to the right. In this instance, we have two imbalanced forces. The horizontal force does not cancel out or balance out the downward force, so the ball should move diagonally and to the right. Now let's see what that looks like around a ball.
If you apply force perpendicular to its motion for a short time, the object will deflect, as shown. Its direction changes. Now let's apply the force again, perpendicular to the new direction. The object deflects again. Let's repeat this process. Now, observe the shape the object traveled. It's very close to a circle. If the time interval of applied force is significantly smaller, you will get a more perfect circle. Which means if an object is always acted upon with a force perpendicular to its velocity, the object will move in a circle. This force is known as centripetal force.
But here, this is based on a downward force that doesn't cause things to speed up as they fall. When we have that, this is what that looks like. If you show that around a ball, it will result in a downward spiral. It's time to get out there and make some noise. Abolish NASA! Let's do this thing! This video has been brought to you by the Flat Earth Institute of Science. Thank you all for watching.